on our website, and we'll send it out to anybody who wants it. They can share it internally, externally, wherever they want. So it's just a good idea that we record this. It makes it easy for us. Good afternoon. My name is Joe Martinenza. I'm an engineer, project manager with the Department of Natural Resources. We are here today because we are coming towards the end of a base level engineering project. We thought it would be a good idea to share this information with everyone in a workshop type format, because not only do we have new analysis, not only we have floodplain models for all Zone A areas within all the Zone A areas that we did work in a watershed. We also have tools. We have tools that you can use to go grab BFEs, and we'll be showing you those sorts of things. We also have a playbook that we're able to give to you, and you can see all the different ways in which you might be able to use this information besides just grabbing BFEs. So this is going to be an introduction to the tools and the engineering and the viewers that we have developed. Okay, Jarrett, if you don't mind, next slide. This is our agenda. We're going to try to follow this the best we can. I'm going to give everyone a base level engineering overview. I'm going to turn it over to Jarrett for a while. He's going to actually start off with a website demonstration. I think that's going to be fairly critical, so you get an idea of what we have out there and how you're able to access it. And then Petia and Megan later on will talk about how to use that data, how to use the tool and the data for all sorts of things. So design, planning, emergency management. I think you'll find at least some kind of use for it, if not all of the above. So, and then at the end, we'll have some question and answers. I encourage everybody, if you have questions as we're moving along, just unmute yourself and chime in, or if you're not comfortable doing that, just type something in the chat and somebody will interrupt me, and when the time is right, and we'll circle back and answer any questions. And again, we'll have that opportunity at the end as well. Okay, Jarrett. So let's start off with, what is base level engineering? Well, really what we're doing is we're taking a large watershed. For those of you who are engineers, it's a Huck 8 size, and we are preparing broad and accurate floodplains. So not just floodplains, but flood risk data, I guess I should say. So this data on our end is useful on many levels. First, we're able to do planning level predictions. So what does that mean? So we've created new models, we create new floodplains. We're able to compare those back to your existing floodplains and say, wow, based on our newer data, which is better, based on the age of your maps and the data was used that went into that, it looks like we need to do some map revisions in these areas. So this is the first step of really coming up with a scope of work if needed for your communities. We are recently going to be recently awarded a grant from FEMA to start doing some mapping in some of these areas, because typically we find in Georgia the floodplains are changing drastically. But not only that, they're changing drastically because we have much better data, and I'll go over that in a little bit. The tools, we wanted to provide tools because outreach is important as well as your job. I mean, you have planning to do, you have, how often do you have a project in the special flood hazard area? And you're like, I need to know the BFE, but this is a Zone A. Well, this data is going to help you, and you can use it right away. As soon as we get it done and we get it posted, you could use it for Zone A areas as best available data. Okay, Jarrett. So why are we developing BLE? Well, besides what I just told you, let's take a step back and kind of look at what are the goals from the FEMA standpoint. Now, at the state, we work with FEMA through a grant. They provide us with a grant and funding to do the work. So we take their goals and then we expand upon them as needed for our state. So we want to continue to build a digital inventory. Here in Georgia, we have digital floodplains for the entire state. So that's already there. What we don't have is a model for every floodplain. And that's where a lot of your zone A's, especially the ones that we've been studying, that's why we've been going back in here. Our goal at the state is to have a flood model for every single floodplain in the state. That way, you don't have to worry about developing BFEs. We can provide that data to you, and then you have the data in front of you, and it just makes your life a lot easier. It also makes life easier when you have development and they need to revise a model. We have a model they can use as a starting point. You have something in front of you that you can kind of see, yes, okay, now they're taking this model and they're adjusting it correctly. Communication, this is going to be a great communication tool. I've already talked about the easy to use tools that Georgia wanted to provide. So it wasn't just enough to do the engineering. Since we have all this great engineering and we're spending millions of dollars doing it, well, we might as well make sure we use every single bit of it that we can. So if there's an output that we can use and put on a viewer or do something else with to make everyone's life a little easier, that's what we've done here. And then also we're able to support communities, questions and concerns with this data, because those of you in the community, you always get projects in zone A areas and you're not quite sure what's going on or what to do, or, you get information in from an engineer and you're not sure if it's quite right, or, whatever those common problems may be. But now you have something you can take a look at and help you with that. Okay, Jarrett. This is a map showing the watersheds where we're currently doing base level engineering studies. You can see the green ones are the ones that we have completed. These are already available up on our dashboard that Jarrett's going to be doing a demo on here in a few minutes. The blue ones are in various stages, but for the most part, they are very far along, and some of these are almost complete. So we've been working on this since 2019. That would be the green area down there. And then 2020, 2021, we've picked up some additional watersheds. It is a fairly massive effort, and I think that it's going to be worth it in the end. Okay, Jarrett. So animation, beautiful. So how did we come up? Well, we did a combination of one-dimensional, which is your more, traditional modeling up to this point, but we've also did some two-dimensional modeling as well. So everything starts with LiDAR. Here in the state, we have flown LiDAR for the entire state. We have received a large portion of that LiDAR, and what we haven't received, we will get. But everywhere we're doing studies on that previous map that I showed you, we do have brand new LiDAR. For the two-dimensional BLE, we do rain on grid modeling. So what is that all about? So for hydrology, we do it in one of two ways, depending on recently, in the past year, HEC-RAS has gone from HEC-RAS 5 to HEC-RAS 6. HEC-RAS 5, we had to do the hydrology outside of the hydraulic HEC-RAS model. We use HMS. We used the curve number loss method. So basically, we took land use data, we took land cover and impervious data, and we figured out what the loss method was. In other words, as the rain falls, it hits the ground, a certain amount of it is infiltrated into the soil. The rest of it is available for the flood. So that is what we want to capture. We want to capture how much is actually running off from the storm. So what we do is we apply the rainfall across the entire area, and we use this curve number loss method to determine what that excess runoff is. The only real difference between these two, computationally wise, is, well, two differences, I guess. HEC-RAS 6, you can do the hydrology within the model, which is very nice. But also we have access to the 2019 NLCD land and impervious cover now, where we were using 2016. Now, things don't change all that much, that often. So in most areas, so it probably doesn't make too much of a difference, but we do have the most available. For the 2D model itself, we start off with a grid size. You can kind of see there in the animation, those little thin black line cells. Those are 250 feet by 250 feet. The thing about cell size is what a 2D model does is it calculates how much water is passing through each of those faces. So it does a computation at each face. The smaller the cell size, the more faces, the more computations it has to make, the longer it takes the model to run. So you got to find that sweet spot. So we start off with a 250 by 250, and then we adjust it as needed. So if we see an area where we need more detail, we'll make those cells a little smaller. If we don't need any more detail, we'll just leave them at the 250. There's other things we can do, and I'll show you on the next slide, actually. We do take a Manning's N number from a raster. We take that right from NLCD. Channels are manually added, and we do calibrate the model to the regression estimate. So as I said before, we use rain on grid to develop our storm, and then we distribute that storm over a 24-hour period like you would normally do, and then basically having the peak somewhere around that 12-hour mark. But that peak really needs to match, needs to be calibrated back to the regional aggression to make sure that we're not putting too much flow into the system or not enough based on the regression estimates. Okay, Jarrett. We have increased detail from traditional BLE. So traditional BLE, you do this and you just run the model and you get an answer based on the terrain and all those things I just mentioned. But there's some things we do in Georgia to help better define those models more accurately, and they make them more accurate in a lot of ways. And it also gives us increased confidence that we can come and remap your community and know that we're using really good data. So the first little picture there is a raw 2D mesh. Remember the little squares there, and through the middle of that, you can see, well, behind it, you see the LiDAR, and through the middle of that LiDAR, you can see a road. Now, remember I said computations occur at each of the faces. So that very middle square, and I don't know if Jarrett can point to it or not, where the road isn't really, well, there's several squares, not that one, the one, yep, those two right there. The road is in the middle of the cell. So when the cell does a computation across those faces, it doesn't even realize there's a road there. So that that will cause the floodplain not to be as accurate. So what we do is we automate break lines development, which means we put a line across that road. We're basically making a cross section across that road, and then we're redoing the cells around it. So now you can see those cell faces. One, there's much more of them, and two, there's a face along the road. So every cell has a face on the road. This will allow us to actually make sure that the water, as it comes down, it hits the road, it's able to back up behind the road because it's calculating there. If you look at that third one, we also burn the channels in. So we use the aerials to kind of estimate the size of the bridge or culvert opening, and then we can burn a hole in that LiDAR, because what the LiDAR is picking up is the top of the culvert or the top of the bridge. So basically it doesn't realize there's any way for that water to get from one side to the other. So we burn that hole in there. It allows the water through. Now we've got a really good model representation. So we do that. We do that everywhere in the watershed just to make sure that the water's moving and backing up in the way it should. Okay, Jarrett. 1D BLE, so that was our two-dimensional. That's stuff that you may have never really seen from us because it's something that's really gaining popularity in FEMA because it's so efficient. So it is more inexpensive to do it because it does it on such a wide area. But 1D BLE, where it makes sense to do that. Well, let me back up real quick. The 2D BLE we use in areas where there is very little relief, there's not much elevation changes in the watershed. As you know, being in South Georgia, a lot of times your areas are flat. You don't really know which way the water's going during a flood. That's where 2D is helpful. Where you have fairly well-defined channels and good rolling topography, 1D is definitely the way to go. For that, we use USGS regression equations. If there is no gauge data, if there's gauge data, we'll do statistical analysis on that and then make sure we calibrate it back to the regression equations. For all of our work, we calculate the flows for drainage areas up to a half a square mile. And you'll see that as Jarrett is running through the thing. You'll see all those beautiful floodplains we developed for you. We do put in the embankments. We put in the openings in a very similar way that I mentioned in 2D. We cut a hole. We burn a hole for the culverts. We make sure the roadway is placed in there. I think that's good for that one, Jarrett. So now we have 2D or 1D engineering models. Now all left to do is just create the floodplain so we can use it for planning purposes and developing the scope, like I mentioned earlier. Again, we take those floodplains, put it right back on top of the models, put it right back on top of the LiDAR and come up with the floodplains. And we don't make a big effort in cleaning up the floodplains for the base flood elevation. It's not necessary at this time, and Jarrett will kind of point that out to you. But we do have, as you can kind of see this map here, there's, you got your blue, which is your primary 1% floodplain. Then you have a bunch of areas that are either less than a square mile or the average depths are less than a foot or both. And not all those yellow, orange, and red areas need to show up on a map revision. They just don't. Some of them definitely don't. Some of them really don't. So don't worry when you see these maps for your area. It doesn't mean if we change your maps, this is what your new effective special flood hazard area is going to look like. We will meet with you ahead of time, talk through this with you, and come up with a good game plan. At a minimum, it'll be that blue area because that's what you would traditionally see, which is greater than a square mile drainage area and fairly well connected. We do all the same recurrence intervals that we do for any of our studies. So the 20, 10, 4, 2, 1, and so on. We also do 1% future where appropriate. Some watersheds are built out, or some areas of watersheds are built out. There's no point because there's no difference between future and present. And we provide the BFE +1, +2, +3 as a tool for kind of looking at your development and looking, to make sure that if you see something where there's not much difference between the +1, 2, and 3, well, then, you might know that one thing, but if there is a big difference, it might, sway when you're talking to developers and the conversation to a different direction. Jarrett? I'm going to stop there, and I'm just going to ask real quick if there's any questions from anybody on that. Again, we can ask at the end as well. Okay, Jarrett, I'm going to go ahead and pass it off to you to take us through the next few.
Okay, thank you, Joe. We did get one question from Mr. O'Neill about how he can access the LiDAR in its raw format. And so Jim Kilnowski just responded to that to give you a path for that. It's also going to be in the demonstration how you can access it in a couple of ways. And so there's going to be two parts to the website demonstration where we'll touch on how you can access that data.
Thank y'all.
Sure. It's essentially the raw data is hosted on USGS FTP servers, but we've got links and avenues to get to it as well. So I'm Jarrett Mattli, a project manager, GIS project manager with Dewberry, and so I'm going to be initially walking you through how you can access the BLE data through the state's BLE homepage and dashboard functionality. So I'm going to run through these next few slides pretty quickly and try to pivot as quick as possible over to the site and give you a more thorough rundown of those functions and resources that are available to you. But everything is centralized on one BLE homepage for Georgia. And so you can get to lots of good educational resources and information. Our status viewer for the latest status of our analysis and what's been posted in our dashboard. And the dashboard's where our true functionality is for generating reports and getting flood hazard information where we've completed our analysis. And then we've got a playbook as well. So I'm gonna come back to those. So this is just a peek at the dashboard and report functionality, allowing you to use this BLE, compare it against the effective analysis, and generate a pretty thorough report of flood risk information for individual properties. And then for our base level engineering playbook, this is essentially a PDF guidebook intended to support communities through how they can use and leverage this BLE analysis in conjunction with their effective published products. This entire workshop is kind of geared to mimic that BLE playbook. So through this workshop, you're getting a lot of the particulars through this, and hopefully that serves as a reference resource down the road. But as I said, we're going to pivot over to the website itself, and I'm going to give you a very thorough demonstration of all the ins and outs of it. So on the BLE homepage, you've got 3 buttons up at the top, and I'm going to come back to those. Just below that, we've got a very brief summary of what BLE is, as well as a fact sheet. So you can click that and open and read through frequently asked questions regarding BLE and its uses. And then below that, we've got a pretty detailed additional outline with videos and images and so forth to help folks understand what BLE is and how it can be used. So lots of good information, tutorial information, tutorials on how to use the dashboard and website as well, and reporting functionality and so forth. And so I'm going to go back up to those buttons at the top. For current status, you'd want to go to the BLE status viewer. And it shows what Joe had showed just a little while ago, where we have data that's been posted on the BLE dashboard. That's the dark green. And then we have data engineering that's been complete but not yet posted. We're still working to get the southern portion of Itchway, Nocheway. And then where we have ongoing watersheds as well. And so this should continue advancing eastward as the next year progresses. Now we just did for the dashboard, we just did in this last week a very large update, including the Lower Flint, Kinchifuni, Muckalee, and Lower Chattahoochee watersheds. For some of those new areas, we are still working on updating cached layers in them. And so if you're going to the dashboard for those particular areas, just be patient with it. It may be a little bit slower in those areas. There may be certain functionality that's that could struggle over the next couple weeks, but we're working to get that all buttoned up and working, and should have that within the next few weeks, barring holiday schedules and so forth. So go back to the homepage, and we've got our dashboard. Let's come back to that because it's going to take a little bit more time. Our playbook, as I said, is a PDF document guidebook. That section out, you'll notice that the sections very much mimic this workshop. And it's got lots of good topical information, as well as it leads you through for each of the different sections what you can do when you have certain combinations of effective data and BLE data, and ways that you can leverage the two data sets or products that you have. And then we'll go to the dashboard itself. So it starts off with just a disclaimer, a simple disclaimer, and then you can already see the data that's been posted and is available to you. It starts off by showing, if I zoom into one of the areas, it it starts off by showing you the 1% BLE floodplain, as well as the 0.2% or 500-year, the 100-year and 500-year BLE floodplains. There's also these masks in place, and those are meant to cover up areas where you have detailed study results in your affected FEMA products. You should not be using the BLE information in those detailed Zone AE areas. And so we're trying to help by masking that information and directing folks to their effective products in those scenarios. And then as you zoom a little bit closer in, you'll notice that we have building little houses. These are correlating with building footprints, where we have taken building footprints and run them through some processes to plug in a lot of the good flood risk data into those houses and use those to serve as the impetus for a reporting mechanism that we have on this site. Over on the left, we've got a dynamic legend. So you'll see that it updates as you turn things on and off and as you zoom in and out. So we've zoomed out, the building footprints have disappeared, so that's fallen off the legend. If ever you are confused about what you're seeing, definitely turn to the legend and see if it maybe helps explain what is on the screen. Up at the upper right, we've got a collection of quick buttons. The first of which is the base map gallery. And so you can click on it and it gives you a wealth of different base map options that may help with viewing the pertinence in the area that you're researching. You can switch to aerial imagery or different vector-based base maps. And then you just click it again to close that little pop out. We also have a search function where you can search for addresses or place names. I believe also, if there's a specific stream that you're looking for, you could search for that, and hopefully it'll take you to the right place. And below that, we have an overview window that shows you generally where you are within the state. And so you can kind of zoom in and out on that. And as you pan around, it should update on the fly as well. So you can click to toggle that off. And then we've got an expanded layer list. And so this is where you can turn on and off layers. We've got additional layers in here for informational purposes that maybe don't come on by default. And we'll start with, you see this little eyeball symbology. If it's open, then that layer is currently visible. If it has a slash through it and you click on that, it turns that layer off. So maybe you only wanted to see the 500-year results from the BLE. You could turn off the BLE 1% 100-year results and see that. You can also turn on the effective flood hazards if you wanted to see that, and we'll turn off the 500-year and turn on the 100-year BLE results again to see that for comparison. Maybe slow with the meeting going on, but all right, I'm just waiting for some of these areas to kind of freshen up. Oh, it's not going to cooperate for me. Okay, so we have the effective analysis. This is one of the areas that wasn't updated, so it should be refreshing, but it seems like it's got a little bit of a lag even here. So, all right, so let's just keep trucking without that because there's other ways of viewing that same information. So now we also have an effective to BLE change layer. And so let's turn off the BLE 1% and we'll just turn on the effective to BLE. So this is where we've taken the base level engineering results, the 1% results, and we've spliced them with the effective 1% results, and you can see the changes. And if you look over here in the legend, you can see where by comparison of those effective flood risks, you have flood risk increases. Decreases, these are horizontal increases and decreases and no change at all. So the decreases would be in green, increases in red, shown there. As you zoom out to broader study areas, I'm going to change the base map to something a little bit different. Then maybe it'll help those changes stand out. As you zoom out, you can see a notable difference in some watersheds, where some watersheds just have a ton more information. And in those watersheds, it's likely a 2D study area. And we literally study the entire area and get results for everything. And so that's why the information is more dense. But even in our 1D areas, such as here, where it's not quite as dense, there may be quite a bit more information than your effective flood hazards, where we've looked to have a consistent analysis up to the 1 square mile drainage area. And so it might go a little bit further up the stream network than your effective products. Now for the 2D areas where we have all this dense information, we're also subdividing the 1% results, and that's also plugged into here. It is the BLE 1% floodplain potential moderate risk areas. And this is something that Joe was touching on, where we're adding a hash pattern to show areas that are under 1 square mile drainage area, areas that have less than a foot of depth. Subdividing those out, just in the off chance that we can show those areas as moderate risk in a future revision. There's quite a bit that goes into that decision, but that would be the benefit potential of having those segmented out before we get to a future risk map revision to incorporate these results. All right. So we also have, just a little bit further down, I'm going to turn those things off. We've got water surface elevations. Those are kind of a smooth grid result, and so you're not getting a lot of variation in those. Those aren't particularly pretty, but there's a way to extract out BFEs if you need them, and I'll go through that here shortly. You also have depth grids for all the different frequencies that we've studied. These would be a little bit more visually appeasing, showing the variation in depth in the floodplain. And then last, oh, well, close to last, actually, we have a collection of depth, or excuse me, probability grids. We've got a percent annual chance grid, which shows the probability of flooding in any given year. And then we've got a probability, a 30-year probability grid, which is the probability of flooding within a 30-year period. And that's supposed to hit closer to home for folks who may have a 30-year mortgage, letting them know the flood potential over that 30-year period as well. So those are on there. And then I said last, but what's truly last is back up at the top. We've got a different spin on those building footprints, where turn off the probability grid, and I'm going to turn on that effective to BLE change layer again. So you can see the building footprints and how they overlap the flood hazards. You can turn those building footprints off, and you can turn on what we have is building risk change, where we have those building footprints coded and symbolized based on the change. So they're green where they have had a decrease in the horizontal decrease in the floodplain, and red where they have an increase, and gray where they have no change. And I know that this particular point is not it would signify that it would be in a decrease area, but when we're doing these processes and plugging into information to the buildings, we're actually using the building footprint itself, and which is going to cover a little bit more than the point, obviously. So and then last, we have a data download function here, and this is one of the answers to Steve O'Neill's question, where one of the layers that we have available is the ground DEM. It is a post-processed DEM derived from the LiDAR, but it's the DEM that essentially we're using for our analysis, which is, coming from that LiDAR. And you can download any of the data sets that we have here through this last little widget. And so that's this extract data function. And all you would do is open it up. You'd pick which method you want to use to draw a polygon. And so if we do, there we go. A quick little polygon using that utility around a specific area. So there we've got an outline of where we want to extract data. You can choose the output format for the vector as well as the raster information. And sometimes it gets a little carried away where it starts bringing up our report functionality, but it's doing that too quickly. I'm coming to that. I'll come back to that. But and then you've got a list of all the different layers that you can extract. So you can extract out the 1% water surface elevation grid, the 1% depth grid as an example. Maybe you want one of the probability grids as well as that ground DEM. So once you've checked everything, you've set your data formats, you've drawn your polygon, you hit the extract button down at the bottom, and it'll give you a download of that data. All right, so let me go ahead and clear out that polygon. And let's take a look at our report function. So if you click anywhere within the viewer, it brings up our report functionality. And I'm going to find a decent property. There we go. We've got a little bit of red up here with some buildings that have been added to the floodplain. And so if you click on a building footprint, now you don't have to click on a building footprint. You can click anywhere to get informational returns from our reporting mechanism. But I'm going to do, for demonstration purposes, a particular building. Give it just a second to pull up our report dialog. Okay, so here we have our BLE dashboard report mechanism. This is a BLE summary, if you will. When it comes up, you get two map viewers at the top. They are synced, but they are showing slightly different information. The one on the left is giving you the 1% and 0.2% 100-year and 500-year flood hazards from the BLE analysis. The one on the right is giving you the change information, which compares the effective 1% and the BLE 1%. Now, there is a layer list that if you wanted to show something different in one of these, you could change that. Same method by turning something on and off by clicking on the eyes. You can also change the base map. Maybe it's easier to see this property in question using aerial imagery. So you could do that. And then you can zoom in a little closer, but if you go in too closer, the data might disappear, and that's due to caching limitations. We also have below that a legend showing all the different symbologies for the different layers that could be turned on in those map views. And then if we keep going below that, we've got initially some high-level information from the county where the property is located, the watershed, the firm panel, the effective firm panel that's associated with the property. We're also pulling the estimated BFE, base flood elevation, from the BLE, from the 1% results. We have the effective and BLE risk, and so you can see a comparison whether they're maybe outside of this particular property is low risk in the effective because it's outside of the 1%, but we can see in the BFE that it's actually in the 1% results. And then the lowest adjacent grade, that's strictly pulled from the LiDAR, no adjustments or buffering applied, and that's applicable to one of the sections that I'm going to go over in a little while. And then down below that, we've got the depths and water surface elevations for all the frequencies that we've studied, as well as the probability of flooding, both the percent annual chance and the 30-year probability grid results. And so you can see, I said that the 30-year probability results communicate a little bit better for those who may have a 30-year mortgage. It tends to be for properties in the floodplain that it's a bit higher when you're compressing over that time period, and so that's where it may hit home a little better, or communicate better with a homeowner. So at the very top, we also have a printing function for this BLE summary. And so you can choose between a portrait or a landscape document and hit print. And what it's going to do is generate a PDF-based report, giving all that same good information, leading with that BLE summary map, giving the BLE summary information, then going into showing the changes between the BLE and effective data, and then some disclaimer information and notes, and then definitions of effective flood zones for reference. A lot of good information there. Across the top, we've got a couple of additional tabs. So it defaults to the BLE summary tab. And so that's where we are currently. There's this zoom to. So if you get out of focus on the main map viewer, you can use this zoom to refocus on that particular property. There is a Loma view, which I'm going to go back to the PowerPoint slides and come back to this particular function and tab. And then we've got an effective risk and flood model search function. And those are taking you to, these were two separate map viewers, but they're since been very recently been combined into one map viewer. I think the effective flood risk one, we have to update the link to that, but the flood model one takes you to the same place, where it takes you to the state's primary map viewer, which shows the statewide effective mapping results, and as well serves as our platform for being able to download effective models where it's available. Right, and then we're going to pivot back to the PowerPoint, and we'll come back to the map viewer shortly. I'm going to refresh it by hitting reset so it's ready. Here we go. All right. So now we're going to start with the first section of the BLE playbook, talking about how BLE can be used for floodplain management purposes. And BLE can be used in several different floodplain management activities, but specifically in areas where you have Zone A on your effective products with BFEs not readily available, or in areas where you have no special flood hazard area identified on those effective products, where there's no flood hazard results. Particularly in these 2D areas, we're going to have a lot more flood study results for you to use in those areas. It can also be used to support, trying to get my taskbar to disappear. I'll just go with it. So you can also use BLE for any number of permitting activities. So the NFIP requires communities participating in the National Flood Insurance Program to permit all development, review all proposed development, and ensure that new development takes place in a way that's reasonably safe from flooding. And the BLE can help with all of those things, particularly in using the water surface elevation from the base level engineering to guide new building construction, substantial improvement and renovations projects, as well as repairs to substantially damaged buildings. And so the website can give you that supporting information through our reporting mechanism, as well as through the data extraction mechanisms. We also hope to make the engineering models, the underlying models for the BLE available for download. So that's something that's been in discussion, how we want to make that available. But that currently would be available through request if there's a developer or community who could use that and they want to test out scenarios from a new development, they would be able to leverage that information as well. Then the BLE can help with any number of better enforcement activities, particularly before it gets published on the regulatory products. It's flood hazard information that goes above and beyond the effective products. And so there's one layer I realized that I forgot to cover is the freeboard layer that we have on the map viewer. So that's a toggleable layer that shows you where an additional 1 foot, 2 feet, or 3 feet of flooding will go above that base flood elevation. And so if you have freeboard requirements in your floodplain management ordinance, you can use this information to support that regulation, or you can use that information to see if it would be palatable to update your ordinance to adopt an additional freeboard requirement in your community. Maybe starting out with +1 feet, requiring new construction above 1 foot of the BFE. It can be used to support planned unit development. I can't get that to go away. Okay. It can also be used to support plan unit development decisions, looking to reward developers who avoid the placement of new parcels and development areas in and around the floodplain, not just using your effective flood hazards, but the BLE flood hazards. It can be used to support open space preservation projects, looking at those areas where you have large increases in the horizontal floodplain based on the BLE analysis and seeing if those undeveloped spaces are places that can be acquired and preserved for preserving the natural flood hazard area. And it can also be used to inform the placement and protection mitigation activities, supporting and protecting critical facilities as well. And when we talk about better enforcement activities, it's good to also consider participation in the community rating system. The NFIP CRS rewards communities for going above and beyond the minimum NFIP requirements. Since the BLE does cover a lot more territory than the effective products, and it's not currently part of the effective products, there's a lot of ways that you can use this to secure CRS credit. Now that might change a little bit. You've got to track the things that you're doing that are above and beyond in the right way to get the credit. If the state decides to move forward with incorporating some of those results in the effective products, then that might change a little bit in terms of the flexibility. But currently, they are a separate product, and so therefore might be able to be used for CRS credits. And one of the ways that you can use the BLE analysis is through targeted outreach activities. Conducting targeted outreach activities for properties that aren't just in the effective special flood hazard area, but are otherwise at risk. And so you can use that BLE to determine that. First and foremost, looking at the properties that are at risk, that are above and beyond your effective analysis, areas where your effective flood hazards don't reach, and looking at those properties and letting them know that there's a risk and encouraging them to purchase flood insurance. You could also look at properties that are in the 500-year floodplain. A lot of these Zone A areas where we're targeting this information, when they were conducted, it wasn't required to have a 500-year floodplain and water surface elevations and results for those effective Zone A areas. And so that's going to be something that's new in this BLE information, where you'll have that 500-year moderate risk information. And also looking downstream of high hazard dams, looking at those residents and properties that maybe are on the fringe of being impacted by either the BLE or effective information, But if there was an unfortunate dam breach scenario, they would very likely be at risk. So there's probably an added risk in this sort of situation. The base level engineering can also be used to support LOMAs using the water surface, the 1% water surface elevation from the base level engineering results to support LOMA applications. This may require a community supported BFE letter. So as this becomes BLE becomes more widely used and prevalent and available, you might find that there's requests from developers and folks to seek out community support, supported BFE letter. Now, kind of started to touch on this a little bit. This isn't really BLE applicable, but it's applicable to the LiDAR that we've used to support all our BLE analysis. It's another way of looking to use that LiDAR information to support communities and LOMA applications. You can use LiDAR to pull lowest adjacent grade information, but there's a couple of requirements where you need to enforce a buffer requirement depending on whether you're using contours to get that lag or whether you're using raw LiDAR LAS points to get that lag. And that's just a way of sort of acknowledging that while LiDAR is highly accurate, it's still not quite to the same standard as a survey. Survey would traditionally be used for those lag elevations. And so we have a secondary report on the BLE dashboard where we're using this contour-based method to enforce a buffer and extract out lags for properties. And so this is where I want to pivot back to the site. And I'm going to look up a property that I know that's in around Boston, Georgia. So here we've zoomed into Boston, Georgia, and just south of that, I have a couple properties that in the BLE, they look just fine outside of the flood hazards. And you could kind of see from the prior base map that was on there, there's a little bit of a hill here. So it makes sense they're outside of the floodplain. But if we were to turn on the effective flood hazards, you can see the effective zone A in the area, and this layer is not wanting to refresh, or at least not quickly. And so I'm going to be a bit impatient and change over to turn off the BLE 1% and 0.2% results. And I'm going to show the increase decrease. So the effective zone A essentially follows this gray area and the green. And so it's fully encompassing these two structures, or I think there's maybe three structures there actually. And where we have the green, our BLE is reducing the horizontal extent of the floodplain. Where we have the red, we're increasing the horizontal extent of the floodplain. And so based on the BLE analysis, this property is not in the 1% results. And so if we click on it, and give it a chance for our reporting mechanism to come up, we're going to go to that LOMA tab this time. This LOMA report is intended to give you all the information necessary to submit a LiDAR-based lag for a LOMA application. And we'll check into this. For some reason, the effective layers are either being slow or just not generating. We don't have the change in here, but it's giving you the data of this report. It's giving you the location of the property, the coordinates for the property. It's giving you the estimated BFE based on the BLE analysis, base level engineering analysis. All right, and then it's also giving you the LiDAR-derived lag elevation, and this includes the buffered elevation, so it's not straight from the ground. We're applying that buffer, that contoured buffer for FEMA's requirement to use that. And for this particular property, with that buffer in play, we're showing that the lag of the structure is higher than the BLE water surface elevation for the 1%. We also have the date of the LiDAR, the LiDAR source referenced in the elevation datum, vertical datum, a link to the data source, in this case is the NOAA LiDAR data set, and then the accuracy level. So that's the other requirement. To use that LiDAR for lag, it needs to be, I believe, QL3 or better, which all the LiDAR that's been collected under the USGS 3DEP program, as an example, is going to meet that. In this particular case, the NOAA data is meeting that requirement at a QL2. QL2 is actually better than QL3. And then below that, we've got instructions for submitting a LOMA application. And then up at the top, we have a report function here. So you can pick between a landscape and a portrait report, and you hit print. And it's going to generate a similar PDF report. It's going to give you all this good summary information, a map view, disclaimers and notes, as well as the LOMA submittal instructions. Here we go. That's strange that the effective floodplain shows up a lot quicker here. But anyway, so we've got our map with our contours. You've got all your summary information for the BFE, the lag. You've got your LOMA submittal instructions, a sort of checklist to support you through that workflow. And then we've got our disclaimers and effective zone definitions. All right. We're going to keep trucking with the PowerPoint. So it's important to note that the BLE analysis cannot influence flood insurance rate. It is separate. It is not effective, so non-regulatory currently. It can be used, as Joe mentioned, to update the effective products down the road, and may be used for that purpose. So that's something that the state is starting to look into and pivot towards how it can be used to update risk map products in these areas. Now, it can be used to support LOMA applications, letter of M.A.P amendment, and that would, if successful, would remove a structure from the special flood hazard area and thus remove the mandatory purchase requirement for flood insurance for a property. But that would be the only way. Otherwise, it's not being used to influence. Flood insurance was recently revamped through Risk Rating 2.0, which is an NFIP initiative. And it was revamped to consider multiple data sets, data sources to derive at better flood insurance ratings. But BLE, base level engineering, is not one of those data sources. As you consider using the BLE analysis, it's good to also take a look at your ordinances and make sure that they're updated and contain the necessary language that allows you to use these data sets. If you are using the state's model ordinance templates, it very likely already has that language. But if you have any questions, I would encourage you to reach out to the Georgia DNR Floodplain Management Unit staff. We have on georgiadfirm.com the model ordinances posted for your review. You can compare that or ask questions of the DNR, and I'm sure they'd be glad to help with interpreting some of the language. But some of the giveaways is when it references other supporting data, standard engineering analysis, elevation data available to obtain, review, and reasonably utilize. So those are some of the indicators that allow for more flexibility, particularly in Zone A areas. And so with that, I'm going to open up for question, but I want to a couple things before actually we do that. I just want to remind folks that if you would, please, if you haven't had a chance to, please add your name, CFM status, community affiliation, and email address to the chat box. This helps us with general attendance, but also with trying to track CFM credits and giving you a certification for CFM credits. And then we also have to support the credits so we can maximize the CFM credits that we're giving you. We have a couple poll questions. This is the first of two. The other one's going to be towards the end. And this particular question, if you could answer it on your screen, should have popped up on your screen. Also in the chat, there's a dialog box where you just click the true or false radio button and then submit your vote as a last resort. If it doesn't come through or you're unable to use those radio buttons, you can put in true false in the chat. But try and use the poll function if you would. And the question is, base level engineering data can be used to replace Zone AE information on your effective flood insurance rate maps. And no judgment on the answer. Oh, we've already got 100% participation. So great, and everybody seems to have gotten it right. So we're good. All right, so at this point, we're entering our first break, and so we're going to give 10 minutes before we carry on with the presentation and demonstrations. But we can also take any questions. If there's any questions in this moment for Joe or myself. All right. Well, then we'll go ahead and go into a break. I see we are about 5 minutes over, but that should be fine. So I think we can give 10 minutes. And so maybe we'll come back at 2:45.
Sounds good.
Right. So I'll kind of go off camera and mute, and we'll start back up at 2:45. right, Petia, are you online?
Yes, I'm here.
All right, so we'll continue on to the next portion and we'll pass the baton to Petia Doubrovska.
I just wanted to make sure, thanks, Jarrett. I just wanted to make sure that everyone can see my screen just fine.
Yes.
Yes.
Perfect.
Yeah.
Okay, thanks, Jarrett, once again. And with the next several slides, we're going to cover some application of the base level engineering analysis for various purposes, and that can support community officials, developers, and engineers make more informed decisions. And something that I wanted to point out that the base level engineering analysis is developed, and all the products, supporting products developed as part of the base level engineering analysis are available for community official and developers to download from the BLE dashboards. But the use of this base level engineering analysis and the estimated BFE is not required. The information, though, is available and can support, again, community officials take more informed decisions and make sure that they're building more resilient community and are minimizing the flooding risk. Also, currently, the results from the base level engineering analysis are not replacing the information that is included in your effective firm products and effective firm maps, though the base level engineering analysis is developed that meet all requirements and regulation, and in the future can be used to update the FIS, the flood insurance study report, and also the firm maps for your communities. Since the base level engineering analysis is available and the data is available, and multiple departments in the local communities can benefit from using this data, we recommend sharing this data between the different departments in your community. The data again includes like the actual modeling data, hydrologic and hydraulic modeling data, but also some of the supporting data sets like the various floodplain mapping for multiple events, the depth grids, the water surface elevation grids, the probability grids that Jarrett was showing you previously. All that is available and can be used by different departments in your community. The first application of the base level engineering analysis is for zoning planning. As you have already saw, based on what Jarrett has showed you, the base level engineering analysis provides spatial and visual information about the existing flooding risk in areas that previously had no information about the flooding risk. And as you can see here on the example, the image on the left is showing you a property which is outside of the effective special flood hazard area. It's located in an effective zone X, but if you utilize the 1% BLE floodplain mapping and you overlay it with the proposed development, you can see that actually a significant portion of this property is going to be included in the 1% floodplain, and there is a significant risk of flooding for these properties. So the base level engineering analysis can basically help your zoning department evaluate their existing zoning maps and also strategically plan zoning updates and future developments to avoid any areas where existing flooding hazard exists. Aiming to reduce the potential loss to property and also infrastructure. The base level engineering analysis can also be used to strategically utilize areas that are included in the 1% floodplain. So one such use of an area can be to designate such an areas as an open space preservation. This way, any development in these areas is going to be prohibited, but also the natural functions of the floodplain are going to be preserved as these areas are designated as community parks. So the base level engineering data sets can be used by community officials to plan any future land developments and also update the zoning maps to considering the existing flood hazard and also to minimize the potential losses in the future. Another application of the base level engineering analysis is for land development planning and any future developments. Basically, currently you have the special flood hazard areas identified by the effective firm maps, which are shown, for example, on this image on the top. Here, they're shown in blue. If you are planning a proposed development in this property here, based on the effective maps, different maps for the community, this property is located outside of the special flood hazard area, and no information about the existing flood risk for this area is known. Again, if you overlay the proposed development with the results from the base level engineering analysis, again, you can see that a significant portion of 1% base level floodplain is passing through this property. So the base level engineering analysis can provide information about the existing flooding risk beyond the effective special flood hazard area for your communities. Along with the spatial boundaries of the floodplain area, something else that the base level engineering analysis is providing is the actual depth grids, which are providing information about the severity of the flooding in the floodplain. The risk and the severity of flooding is different depending on which part of the floodplain are you located. If you are located in the deepest portion of the floodplain, obviously the risk of flooding and the consequences of flooding are going to be more severe compared to if a proposed development is located toward the fringe of the floodplain, where the depths of flooding are not as severe, as well as the velocity are not as high. So we definitely recommend utilizing not only the floodplain boundaries developed with the base level engineering analysis, but also some of the other supporting products like the depth grids when you are planning any future developments. As shown in these images at the bottom, if you have a proposed development, and this is a parcel, if you didn't have information about from the base level engineering analysis, a potential layout of the building, as shown on this first image here, would have put this building at the deepest part of the floodplain, and again, consequences of flooding and are going to be significantly impacting the property and the building if it's placed in this location. But if a development is being checked against the base level engineering analysis results, developer can decide that they can place this building instead of the deepest part of the floodplain in the shallower part of the floodplain, where they can raise this building with significantly smaller amount of fuel being placed. And again, they protect this building from, or minimize, actually not protect, but minimize the risk of flooding if they use the available data to smartly place the layout of the proposed building. Another application of the base level engineering analysis is to support any public works planning. Local communities or various communities, you have information about your infrastructure in your community. And some of that infrastructure can be in a bad shape, can be failing, or maybe not providing the required capacity to pass the flooding. So you as a community official may have to prioritize some of these projects, capital improvement projects, over another. So one way that you can utilize the base level engineering analysis is to overlay your infrastructure inventory data with the 1% base level engineering floodplain and try to identify any infrastructure, undersized infrastructure, which is located in the floodplain. Obviously, this infrastructure will be more critical and should take a priority as a capital improvement project over an undersized structure which is located outside of the floodplain. Just because, prioritizing project that, as you can see here, has a potential for flooding a road. Obviously, there is significantly larger drainage area coming to the structures, can actually help the community officials better plan how to spend the available funds, funding various capital improvement projects, aiming to prioritize the public safety. Another way, again, that you can utilize some of the supporting deliverables with the base level engineering analysis as the depth grids is to basically prioritize any capital improvement project based on the likelihood of failure based on depth of flooding and frequency of overtopping. So obviously, if you have a structure that is frequently overtopped by a significant depth of water, the likelihood of failure of this structure is going to be significantly higher than if you have compared to another structure which is very rarely being flooded and flooded just by, let's say, couple of inches of water. So utilizing the depth grids, you can get information about, okay, how significant is going to be overtopping over this particular infrastructure. And also utilizing the various depth grids, you can also identify, okay, is this overstructure going to be overtopped during the 10% event, or is it only going to be overtopped by the 0.2% event? So basically, the likelihood of failure can also help you prioritize any capital improvement projects in your community. Another factor that can help you prioritize any public works projects is the consequences of failure. So depending on what is located downstream of this capital improvement project, you can identify or basically prioritize one capital improvement project over another. As you can see here on the example, you have a water treatment plant located downstream of infrastructure in the floodplain, versus the second image here is showing that downstream of the proposed capital improvement project, you have just undeveloped area where obviously the consequence of failure is not going to be as significant just because it's not, there's nothing much to be impacted downstream of this structure. So overlaying the base level engineering data with the aerial imagery, or if you have any database or information about the critical facilities in your community, can help you again prioritize the capital improvement projects in your community. Another application of the base level engineering analysis is to utilize the estimated BFEs when you're planning improvement on any roads in your communities, and you just want to make sure that the proposed roads are going to be sufficiently elevated at or above the estimated BFE when another data is not available. The base level engineering analysis can also be used to identify any overtopped roads that are providing the only access to, let's say, residential communities. So you as a community official may basically try to look for an alternative way to access this residential community in case of emergency, or maybe you can plan road improvement just to make sure that this road is elevated and it's not going to be impacted by flooding. Or you may look for if there is a way to construct or develop another access to this development to make sure that an alternative access to the community or critical infrastructure is available in case of emergency. And also, if you have information about any critical facilities in your community, you can utilize the 1% base level engineering analysis or even the 0.2% base level engineering analysis to see if the access to those critical facilities is going to be maintained with during different storm events. So, for example, if you have a pump station, you want to make sure that you'll be able to access the pump station and make sure that it's properly functioning during various flooding events. And if the base level engineering analysis is showing that this access road is going to be flooded for, let's say, the 10% event, you may, again, make sure that you elevate this access road above the design storm to make sure that your access is going to be maintained to this critical facility. And here in the next two slides, I'm going to cover several examples with the proposed developments when they're adjacent or encroaching in an effective special flood hazard area or in the base level engineering floodplain. So the first scenario is if you have a proposed land development which is adjacent but not encroaching on the effective special flood hazard area zone AE or on the 1% base level engineering floodplain. So anywhere where we have a project which is adjacent to an effective special flood hazard area zone AE, the FEMA effective base flood elevations are going to be used for regulation purposes. So they are still they're still regulatory and they're still going to apply. So if you have that scenario, again, a property adjacent to the effective special flood hazard area zone AE, we recommend utilizing the effective DFIRM database to determine the base flood elevation. If you have a proposed project which is adjacent to but not encroaching on the effective special flood hazard area zone A or the 1% BLE floodplain, in this particular case, the estimated BFE based on the base level engineering analysis can be used for regulation purposes. So if your effective special flood hazard area zone A does not have any information about the base flood elevation, the base level engineering analysis provides this information for you. A third scenario is if you have a proposed development which is outside of the effective special flood hazard area, but it's proposing an encroachment on the 1% base level engineering analysis floodplain. In this particular case, we recommend considering evaluating the impact of the proposed development over the flood hazard prior issuing a permit. So basically, evaluating the proposed development for no-rise analysis just to make sure that you're not going to make worse the existing flood hazard near the property. And for that, a developer or an engineer can use the available base level engineering modeling data. The fourth scenario is when the proposed land development project is encroaching on effective special flood hazard area zone A or the 1% base level engineering floodplain. And the base level engineering is the only available study. In this particular case, we're encouraging leveraging the base level engineering as the best available data and utilizing this data to develop corrected effective model and also proposed condition model that reflects the proposed development. and based on these modeling scenarios to evaluate the proposed development for no-rise conditions. If the no-rise conditions are met, again, the development that is not going to negatively impact the floodplain in this area. And the last scenario is when the land development projects is encroaching on the effective special flood hazard area zone AE. In this particular case, the FEMA effective models are still the best available data, should be used for evaluating the impact of the development. You can utilize some of the input from the base level engineering model to validate the effective models. And one of these input is the topographic data. So if you open the base level engineering analysis hydraulic modeling, you will see that there is a topographic data in these models, and you can use this data to basically evaluate the cross-section in your effective zone AE study and see if they're relatively comparing well to the latest available LiDAR topographic data, or if not, if this is something where you want to update the model, or if you want to collect survey data to create your corrected effective condition model for the proposed development. And another tool from the base level engineering analysis that you can use is also the hydrologic input. So basically, you can basically extract the flow from the base level engineering analysis and see how is it comparing to the effective flow for the zone A stream, and just to kind of guide you if you need to spend more time to make sure that your effective hydraulic modeling is still good. Base level engineering analysis can also be used for other applications, and some of those applications is something that Jarrett already mentioned, is if you are applying for letter of M.A.P amendment or conditional letter of M.A.P amendment, letter of M.A.P amendment based on fill, M.A.P revision based on fill. So you can utilize, if no other data is available, you can utilize the estimated BFE to support your LOMAR or LOMAR F application to FEMA. Again, these applications are usually needed when property is inadvertently mapped in a special flood hazard area in the effective firms, because at the time the studies were developed, the topography data wasn't good enough, and some of existing buildings was placed in the floodplain in error. So you can use the estimated BFE to submit for a LOMAR application for if that's the case, and if the building is elevated above the estimated base flood elevation. The base level engineering analysis can also be used to provide estimated BFE if elevation certificate is being prepared. And again, this elevation certificate may be needed for the LOMAR application. Or if floodproofing certificates are required for non-residential building, if there is no information about the base flood elevation, the BLE determined BFE can be used to submit the floodproofing certificate. And lastly, if you are planning to protect service equipment in an existing building in a floodplain, and you just want to make sure that the service equipment is sufficiently elevated to not be impacted by the flooding, you can use the estimated BFE to basically check how high you need to elevate your equipment to make sure that you minimize the risk of flooding. Another application of the base level engineering analysis is for, and in particular, it's the modeling that support the base level engineering analysis, is to develop dam break modeling. Georgia Department of State, the Georgia Save Them program prepared engineering guidance highlighting the requirements for developing a dam break modeling in Georgia. And these requirements are highlighting that dam break studies developed in Georgia should be based on a sunny day dam failure due to overtopping. What this means is that the dam is gonna fail not because of any hydrologic input, so no precipitation or storm event going over the study area is gonna cause the failure, but more the failure is gonna be during a sunny day. The dam is gonna be filled to the top. Any spillways are going to be blocked, and then the dam failure is going to occur. So you can, if your community is interested in identifying the potential hazard in case of a dam failure, the base level engineering analysis hydraulic model can be leveraged to support the development of the dam break analysis. What you need to make sure is that you removed any hydrologic input from the hydraulic modeling, so no information about precipitation should be included in the dam break modeling. And some adjustments should also be made to the topography data to make sure that any spillways, if there are any emergency spillways for the dam, that the spillway is being blocked, so that the Georgia Save Dam program requirements for dam break studies are being met. Information about the breach width and formation time, and also information about the height of the dam and the volume of the dam is available in the Georgia Save Dam program. They have inventory of the dams, so you can get this data from them. And again, you can apply the Froelich equations to determine breach width and formation time to make sure that the study is developed in accordance with the Georgia Save Dam program. And another application for the base level engineering analysis is for sanitary sewer rehabilitation projects. You can utilize the floodplain mapping developed for the base level engineering analysis and also the depth grids to identify any sanitary sewer manhole which are located in the floodplain, and they may experience infiltration and inflows during significant storm events. If you have noticed that suddenly you have increased flow in your sanitary sewer. This can be like a starting point for you to identify any areas where such an inflow and infiltration may occur if you overlay your sanitary sewer infrastructure with some of the products from the base level engineering analysis. And obviously, if you identify these areas where such a potential for inflow and infiltration in the sanitary sewer system exists, you can basically decrease the burden on the wastewater treatment plan and increase minimize the operation cost and increase the lifetime of your facility. And I also have some like a tabletop exercise that I can show you how you can utilize the base level engineering analysis results to identify any overtopped structures in a community. But before I jump into that, do you have any questions? Okay. Okay. So the first step to start this exercise is you have to get to the Georgia BLE dashboard, the one that Jarrett provided significant information how you can use this website to download data. So again, this is the information that is currently available for download. As we continue developing and finalizing the base level engineering analysis, this dash viewer is going to show more and more areas where base level engineering data is available. If you want to download the data for a particular portion where base level engineering analysis is available, you just utilize the extract data button. You select the area. Again, I'm not going to show that, but because Jarrett just covered that, but you basically can select what information from the base level engineering analysis do you want to download for a particular area in your community in order to if you are looking to identify any capital improvement projects for your community. So I have already downloaded the data for Thomas County, and I have loaded it to a map. So the data is already here. And this is the data. What I have selected to download is the modeled streamlines. These are the 1 square mile streams in this particular area. I also have the 1% base level engineering floodplain mapping. And again, as you can see, the floodplain mapping is shown in different colors depending on the drainage area to each location and also the depth of flooding, the average depth of flooding. We have 4 categories of floodplain here. We also have the county boundaries, and lastly, I have downloaded the 1% depth grid. So you can see if you zoom in, this data set is providing you information about the depth of water in the floodplain. So this is the first set of data that we're going to use for this analysis. The second set of data is the roads. If you have any information, if your community basically have GIS data about the existing roads in your community, you can utilize that. If not, you can download road inventory data from the Georgia DOT website. If you search for road inventory, it's going to download. You can see that you have road inventory geodatabase. You can download this data, and this data is going to cover the whole state. So what I would recommend is before you proceeding with this exercise, just clip the road data to just the area of interest or just to your community. In this particular case, this is Thomas County, and I clipped the data to just the Thomas County roads. Something that I wanted to provide information about, this is all the roads within this particular community. And you can see they have a field called functional. This basically provides information about the road class. And just to know which road class is corresponding to each number, I would recommend downloading also this document, which the road inventory dictionary. The page 9 of this dictionary, you can see that depending on the code, what kind of a road you have. So 1 is interstate, 7 is local. So you can add additional field to your roads and just based on the data just shown, populate the type of roads that you have. So a next step that you can do, and I'll turn off some of the base level engineering analysis data, is to intersect the 1 square mile streams with the roads from the GDOT website. And basically the end result of that is going to be points. These points are basically the location where structures are located, and these structures are basically passing the flow from the streams under the roads. These points are later on we can intersect these points with the the 1% depth grids in order to assign a depth of flooding for each of these points. And based on this depth of flooding, then we can export all the data into Excel and try to prioritize and rank the capital improvement projects. Something that I wanted to mention is that before exporting the points into an Excel, I would recommend reviewing them just to make sure that they're in the right location, because sometimes it's possible that the terrain may be a little bit not aligned with the aerial imagery nicely. So just make sure that you review them and make sure that the point is really located on the top of a road. And something else, again, I have a bookmark here. In case where you have a point identified at a location where you have a bridge, and again, I'll have the topographic data here to show you that this the topographic data does not reflect the top of the top deck of the bridge. So any locations where you have such a point in an bridge locations, you can just disregard these points because the depth of flooding is not really the depth of flooding on the top of the deck, but it's just the depth of flooding from the bottom of the stream. So in this case, disregard any locations where you have bridges. So after we export the this shapefile, the point shapefile into Excel, what we have is the depth of flooding. So basically for each, we export the points and we basically remove any points which are not overtopped. So if you see a value of -9999, that means that these points are not overtopped and we remove them from our exercise. So we only kept roads which are really flooded. What we can do next is we can basically rearrange the data from the most severe flooding to the least severe flooding, and we can basically rank our locations and our capital improvement projects. We can rank them from the most severe flooding being the highest, the worst, the most critical point, the most critical capital improvement project, given a depth rank of 1. And the least severe flooding is being ranked as 62. If you prefer, you can add different criteria in order to rank your projects. And some of this criteria is the depth of flooding. So basically, in this particular case, what we have done is like we multiply the depth of flooding based on this value here by 1.5, but we kept it at 10. So obviously from 1 point on, like, if you have 6 feet or 10 feet of flooding, 6 feet of flooding is significantly significant flooding. So at this point on, it doesn't really matter if it goes to 20 feet. It's very critical to have a road with such a high depth of flooding. So we can create this field where we can multiply the depth by 1.5 and cap it at 10. Then we can create another field where based on the type of road that we have, the road class, we assign different score. So if you have a principal arterial road like this one, we score this as a 10. If you have a local road, obviously it's not as critical because it does not provide that much, it provides access, but it's not provide a large volume of traffic going through this road. The road class is 4. Again, for a major collector, we have a road class of 7, and for minor 6. So you just assign a score based on the road class. Another aspect to review is also if they are alternative roads. So if a particular road is providing the only access to a subdivision or developed area, we provide a score of 10. If it provides an access, but there is another access available, but it's flooded, we assign a score of 5. And lastly, if there is another exit but it's not flooded, we score this as 0. And the next criteria is the ownership of the road. If the ownership is if the road is owned by a state, it's a private road or interstate, we give a score of 0. And if it is a road that's maintained by the community, we provide a score of 1. So we combine all these criteria. We basically add the depth criteria, the road class, and the alternative road. We combine all those and multiply them by the ownership. And then we assign the new score for any of those overtopped roads. Again, then we can sort them by the highest score and assign the final ranking. And in this case, the rank number 1 is a structure which is a minor collector. It has 6 feet of flooding, but the score that it gathered was like, the score that it so actually it's not minor collector, it's a local road providing the only access. And the score that it gathered was 23, almost 23 points. So this is just an example of how you can use the available base level engineering analysis to identify any capital improvement projects in your community and also to prioritize them based on these various factors. That's all I had. If you have any questions.
A shorter break to keep things within the allotted meeting time. And so if we want to, we'll take a brief pause and restart at 3:30. And then just a reminder that if you haven't put your name and CFM community affiliation and email address in the chat, please do so that we can track general attendance as well as CFM certifications that we'll send out after the meeting. And so we'll start gearing up to switch presenters, and at the half hour, we'll pick back up. All right, so we'll go ahead and get started again, and we'll pass the presentation over to Megan Hanifan.
All right, thanks, Jarrett. Can y'all hear me good?
Yes.
Awesome. Okay. Yes, my name is Megan Hanifan. I'm a water resources engineer with Dewberry in Atlanta. Most of my experience is water resources engineering, but I have been helping communities the past several years with hazard mitigation grant applications. So I helped out put together this section of the BLE playbook, which is focused on emergency management and how we can use BLE data to support those type of efforts. And GMA also helped us out a lot putting together this section. So big thank you to GMA for all their help with that. I'm going to turn off my video because my screen is over here. But so we're going to start off. This section is BLE for emergency management. Okay, there we go. All right, so the first question that we asked ourselves was, can we use BLE data to support emergency management activities? And the answer is yes, absolutely. There are many different applications that it can be used all throughout the emergency management life cycle. So from before an emergency incident, during, as well as after, BLE data can be used. And so I want to start off talking first in the planning section, planning phase of emergency management, specifically hazard mitigation plan updates. Within the process of going through a plan update, there are a number of different steps, and many of those we can use BLE data. And I'll dig more into each of those. Okay, so one of the earlier tasks as part of a hazard mitigation plan update is to review the community capabilities. What tools are available, what capabilities do we have as a community that can help support hazard mitigation purposes. And so I just want to highlight that this, the BLE data, as well as the web viewer, is a new tool for communities to use to assess their risk and to identify mitigation options. And so one of the really other nice things about using or having this data is that it can be used as best available data in addition to the FEMA firm products. And then communities also have the flexibility to choose if they have BLE data or if they have effective data, which products they want to use, which are more conservative, which give them sort of better results when it comes to these mitigation plan updates. So communities have the flexibility to use BLE data wherever it's available. Okay, so I'm going to go back and forth between the slides and doing some quick demos for you. The first one is something you've probably seen a bunch of times already, so I won't spend too much time on it. But as you've seen, this is the viewer. Petia just recently showed you how to do the data download. But just to review it one more time, when you're in the viewer, you click this bottom button, and then you just select your polygon control, and you can click and drag, select your area of interest, and then select which products you're interested in downloading. Everything from your floodplains to your water surface grids, your depth grids, your probability grids, as well as your ground elevation. And if you select what you want and then you click extract, it'll download a zip file for you. And then you can work with the data in either ArcGIS or QGIS, whichever program you are most comfortable using. Okay, so this is a graphic that GMA provided to us, and it gives an overview of all the different statuses of the hazard mitigation plans for all the communities throughout the state, or the counties throughout the state. And to the left and then on the right is basically the status map of our BLE project. So if you are a community that's starting to think about, updating your hazard mitigation plan, in the 6 to 8 to 18 or 3 to 6 to 18 month range time frame, you can come look and see what products are available now, what products are going to be available, in the next year or two, and plan on using those as part of your hazard mitigation plan update. Okay, so one of the next things as part of a hazard mitigation plan update is to conduct a risk assessment for the community to identify their flood risks, the location, the magnitude, what assets are vulnerable, and what is the probability of flooding to really determine what the risks are throughout their community. And we can use a lot of the BLE products to support that. Some of them include using depth grids to show depth of flooding at structures and critical facilities, infrastructure, and community lifelines. We can look at evacuation routes and see if they are still appropriate and if they're still safe. We can use the depth grids to estimate losses and building damage using FEMA's depth damage curves. And we can also use the probability grid to identify areas that have a higher chance of flooding and a higher chance of flooding more frequently. So let's swap back. Okay, so I showed you how to download all that data from the BLE web viewer. So what I've downloaded already includes the 1% floodplain, the 0.2% floodplain, all the different water surface elevation grids for all the storm events, as well as all the depth grids. And then the annual chance of flooding, so the chance that this is going to flood in any given year. And then also the probability of flooding over 30 years. 30 years is, the typical mortgage length of time. So this is a really good public outreach tool so people can understand over the life of that mortgage, what is their chance of flooding. So if we're looking at identifying risk as part of our mitigation plan update, a lot of times in the past, we've only had our floodplain, just a single polygon, either you're in the floodplain or you're out of the floodplain. But that didn't really tell us a lot of information about the specific structures and what their specific risks were. Either they were in or they were out. But now all these products, like I mentioned, include depth grids. So we could turn on the depth grids and zoom into some structures. And we can start to see that some do have a higher depth of flooding for at least the 100-year event. For example, this structure right here, we're looking at 1.4 feet of flooding compared to this structure over here, that's 0.4 feet of flooding. So this is really helpful if you're trying to prioritize your projects. If you have a lot of structures that are in the floodplains and you don't know, where do you want to put your emphasis, focus your money on, you can use the depth grid to help sort through all those different potential projects, see who is at a greater risk of flooding, and then prioritize that way. The other thing you can check, like I mentioned, is the annual chance of flooding. So for example, here, this structure has a 20% chance of flooding in a single year. If we look over here, this structure has less than 6%. So again, we can use this to rank and prioritize our projects and identify where our greatest risks are within this community. Okay. And then once we've gone through and identified all the risks, the next step is going to be to develop mitigation strategies to help reduce that risk. Again, we can use BLE data to use that, as well as ranking and prioritizing some of those actions. So examples include using the floodplains to inform resilient development, maybe where you want to develop and where you don't want to develop. Using floodplains to identify areas that would be good for potential structure acquisition or elevation. And then using the depth grid to help determine if you wanted to elevate a structure, how high would you need to elevate it for either a residential structure or a critical facility? So talking about using these BLE products for more resilient development purposes. An example of that is actually a really good example right here. You can see these mapped areas are the effective special flood hazard area. This is what's on the FIR map. And you can see none of this area up here has any sort of risk identification at all. But if we go ahead and we turn on the BLE floodplains, we can see now, just because it's not mapped does not mean that there's no flood risk there. So when you have the BLE products working in combination with your effective flood hazard products, you can get a better idea of where it is safe to build and where it is potentially less safe to build. Another example, I'm going to use the water surface elevation grids, and I'm also going to turn on the ground elevation, the topographic data. This was downloaded directly from the WebViewer website as well. If you wanted to, say, elevate these structures, how high do we need to elevate them? You can use the water surface in addition to the ground elevation. You could also use the depth and see, for example, this structure right here, ground is at 264.58. Our 100-year water surface elevation is 266. So this structure, for example, if it were to be elevated, would need to be at least 2 feet higher, in addition to whatever requirements the community has in addition to that. But this is another good tool to help with those the development of those potential mitigation strategies. And this is the same thing you would do for any critical facilities, in addition to the residential structures. Okay, so we've gone through, we've identified our risk, we've come up with potential mitigation strategies to reduce that risk. The next thing, to move towards building these more safe and resilient communities is actually implementing these projects. Communities probably have a lot of projects in their hazard mitigation plan that they would love to implement. A lot of the times the problem is funding all those projects. And so there are a lot of grant opportunities available through FEMA, including HMGP, BRIC, and FMA, that can help fund portions of the implementation of those projects. But to do that, we need to be able to show a positive benefit cost ratio. And so we can use the BLE data to help come up with those benefit cost ratios as well. The first one, probably the easiest one, is to use the 1% floodplain from the BLE data to utilize pre-calculated benefits rather than going through the full FEMA BCA toolkit. And so the beauty of using these pre-calculated benefits is if your structure is located in the 1% floodplain and the value of the house is less than a certain amount that's determined by FEMA. Right now it's $323,000. If you meet both of those requirements, this structure is automatically considered cost beneficial. So it kind of an easy button to getting your BCA, to getting a favorable BCA if you meet those two requirements. So again, using the BLE floodplains where you don't have special flood hazard area is really powerful to be able to meet that pre-calculated benefit requirement. Let's see, the depth grids can also be used to determine the depth of flooding above the lag to support the potential benefits, and then as well as potential savings for monetary losses that would be for with and without projects implementation. Go back. This off and this off. So again, similar to when I was talking about the sort of more resilient planning purposes, without the BLE floodplains here, none of these structures would be able to potentially qualify for that pre-calculated benefit for the HMGP or other FEMA grants. So if you have a structure that now is within the BLE floodplain, it could potentially, depending on the price of the structure, qualify for that. And that's really powerful. It includes a lot more structures that might be eligible for property acquisition or elevation. Okay, the other tool I was going to show you here is if you wanted to come up with basically populate all of the depth for a single structure. You can actually do this through the BLE Viewer website. It does it for you for single structures. If you wanted to look one structure at a time, you can get all of this information from the BLE Viewer website. But if you wanted to do this on a mass scale, basically for all of the buildings in your community, I can show you how to quickly do that. So if you just go to tools and you're going to use the zonal statistics as table tool, your input feature is going to be your buildings data set. Your input roster is going to be whichever of your grids you're interested in. So I'll do the 100-year for now. And then statistics type, right now we only care about finding the maximum. We're looking for the maximum depth that each structure is going to experience for this storm event. And then you just hit run, which I'm not going to do. But what that gets you is a table here for all of your structures that includes the maximum depth. And then you can come here and sort it. And you can really, again, prioritize which projects you really want to focus on or find solutions for. You could do that. This was just for one storm event that I did. You could also do it for all of your storm events and then combine them into a single table, which I've done already. But you can see for each building, all of the depth for all of the storm events, which is something that could be provided to help support benefit cost analysis as well. Right, so then one of the other big pieces for hazard mitigation plan updates is community outreach. And these tools, again, are really valuable for that as well. Making this information available to the public, which we have on our Georgia BLE web viewer website, can help inform and educate residents about the risks, help build transparency and trust, as well as building greater consensus and acceptance within the community for proposed mitigation projects. And it can also be a really great tool in communicating with local elected officials when it comes to planning and budgeting for capital improvement projects. So that all of that was really part of the preparedness phase or planning phase of emergency management. And now we'll move on to talking about disaster response within emergency management. And here within this phase as well, we can use BLE data to help local emergency managers, local officials make quick and sound decisions during an emergency event. We always like to say if you are in an emergency event and you're using these models, it's also really important to have someone there in the room with you that is familiar with working with them. Understanding the inputs and interpreting the outputs can be really, really important if you're going to make emergency management decisions based off this data. But it can be used to simulate real-time storm events. you can use the depth grid during an emergency to understand where areas might be flooded and where you might need to provide assistance. And then also where you might need to prioritize staging of certain resources like equipment, sandbags, detours, roadblocks, things like that. The floodplains, the depth grids, all of that can be used to help make decisions during an event. And then moving on to disaster recovery. After an event, we can also use BLE data to help make communities more resilient as they rebuild. Looking in the short term, the BLE data, the floodplain data, the depth grid can be used to identify areas that you might need to send out relevant information to homeowners on how they can recover. For example, sending out information related to FEMA's individual assistance program for homeowners, or FEMA's public assistance program for public facilities and qualifying nonprofits. You can also, the BLE data can also be used to sort of assess where damage assessments might be required, or where we might need to do some debris removal, or where we might want to go out and collect watermarks. And then lastly, moving on to more long-term resilience, this overlaps a lot with what Petia talked about when it comes to rebuilding. If you are rebuilding a structure that was in a high-risk area that was damaged, using the BLE data to see, like, should it be relocated? Should it be elevated? Should we maybe not build it back exactly how it was if it was damaged? And then also the BLE data for substantially damaged buildings that might need estimated BFEs. BLE data can also be used to support establishing those estimated BFEs. Okay, that's all I have. Are there any questions about emergency management and base level engineering?
And we do have one last poll question. If Megan, if you wouldn't mind going to the next slide. And Jim, are you going to try and trigger this, or do you want me to? Oh, you already did. You're on top of it. There's one last poll question, so if you could respond to that, and if you have any questions, come offline. Okay, it looks like we've got 100% participation there. And if you want to go to the last slide, and we can use the remaining time for Q&A broadly for any of the presenters, as well as if you wouldn't mind, we do have a an evaluation form. Let us know your thoughts about the information that was presented today, how it was presented. Any feedback would be very helpful in trying to craft these for future ones. We will be trying to have a collection of these over the next year. So any feedback or thoughts that you have would be greatly appreciated. So I put a link to that survey in the chat as well. And then I don't know, Joe, if you've got any closing words.
Yeah, well, let me just make sure there's no questions again one more time on any of this stuff. Peeking around to see my chat. I don't see anything in there. Well, thank you for attending. I hope you got something out of this that can help you with your jobs. Even if it's just every once in a while, just knowing this data is out there is helpful. Thank you, Jarrett, Petia, Megan. I really appreciate it. Well done. And if you need any more information, feel free to call or email one of us here on the screen, and we'll be happy to help you out. Other than that, take care, have a good evening, and thanks again.